In section 8.3, we are talking about applications of integration to some contexts from physics. The first problem of physical origin that we would like to discuss comes from measuring pressure. So suppose you have a certain body of liquid, right? And in this body, there's in this mass of liquid, say water, there is a floating shape, right? And this shape, it floats at the depth d. Then you can find pressure at the depth d using this formula here, where in the formula we have density rho of the surrounding liquid. We have g, the gravitational constant, which is in metric units is 9.8 meters per second squared. And finally d, the depth. So if you have something that's submerged in the liquid at the depth d, you can compute pressure of the liquid at the depth using this formula here. Now, what kind of questions can you answer using this formula? You can look at the first example in this section, which asks to find the force acting on a cylindrical drum. And so from the figure, we collect that we learn that the drum is the circular cross section, a disc in the cross section, and this drum is floating at 10 feet under the water surface. We're also given the radius of the drum. Now, what can we do with this information? How do we proceed? Well, the idea is the following. If you think about this drum, right, the disc is oriented vertically in our liquid, then what we see is that because of the change in depth, pressure is different at, say, the topmost point of the drum and at the bottom, at the highest and the lowest points of the drum. The pressure differs, right? Because the depth is different, and so is the pressure. Right? So ideally, what we would like to use is the simple formula, which tells us that force is area multiplied by pressure. Okay. Now, because pressure is variable, it depends on depth, we cannot just apply this formula. Right? So this is basically the same situation as you would be in if you tried to compute distance traveled by an object with variable velocity. Right? If the velocity is constant, you just multiply its magnitude with time and you get the distance an object traveled. Now, if velocity is variable, as is depth in this case, then you have to split time with small steps and add up velocities traveled in these small intervals of time, assuming that velocity doesn't change much. So that's how we get to the Riemann sum. Now, so in this context here, what we will do is we will think of this drum here. Okay, so I have a zoomed in view. Right, so I have a circular drum, and because depth changes vertically, it makes sense to consider the vertical axis. So here I am going to introduce the vertical axis. I will place its 0 at the lowest point of the drum. Actually, never mind that. I want to place the origin in this case. So I could do that. Now, in this case, what I want to do is I want to exploit the symmetry of the drum. So I will actually place origin at the center of this disk, of the side surface of the drum. Okay, so this is my y-axis, and this is the origin on the y-axis. So what happens here is that pressure changes with depth, right? But just like with displacement, when the velocity is variable, I want to to measure forces that arise for intervals of constant pressure. So when is pressure constant? Obviously, when the depth is constant, right? And so that is when we are looking at a horizontal strip in our drum. So for example, in this very thin strip, so it's a thin horizontal strip, the change of depth is very small. And so because of that, I can assume that depth is roughly constant. Right? So this is the change of depth, or equivalently the change in y. All right, so on this thin strip, depth is approximately constant, and so I can compute force that acts on this single horizontal strip. Okay, so what do I do with it next? Well, in general, I want to think of something that behaves as a Riemann sum. So I want to think of force as the sum of forces that come from slicing this drum into a large number of horizontal strips. In general, I will be slicing the y-axis into n subintervals, and on each subinterval, I'm thinking of depth as being constant. I compute the force that acts on the ith strip using the formula over here. Okay, so this is the formula I'm going to use. So I will say, well, Fi is equal to Ai times P sub I, right? So that's pressure that corresponds to this ith strip. So ith strip is situated roughly at the I coordinate y sub I. All right. So what I have here is the sum. So actually, this equality is not precise. To make it precise, I need to take the limit as n goes to infinity. All right. So when the partition is fine, so it's this expression. So what I do next is I rewrite Fi's. So it's the limit when partition becomes finer and finer of the sum Fi. Now Fi, as I just observed, is Ai times B sub I. Right? So then the next step is to express both Ai and Pi in terms of y. So that is our variable. Now what's the dependence here? Well, obviously, I can express P sub I in terms of yi. So how do I do that? Well, P sub I is given by rho, which is assumed to be constant, g, which is also constant, times the depth that corresponds to yi. Now, to find depth that corresponds to yi, here's how I have to think. So so from this picture, the depth at the origin is 7 feet. Right? So I have 10 feet total. The radius is 3 feet, and so I go up here and I get 3 feet up, and so I get at I arrive at 7 feet under the surface of this liquid. And so as a moral, I have the depth di given by the formula 7 minus yi. Right? So that is because, right? So once again, if I'm at the origin here, y is 0, and so depth is precisely 7. Now if y increases, right, so I go up a little bit, so what happens then? Well, depth becomes smaller. So when y is positive, di is smaller than 7. So this is what the minus sign here accounts for. Right, so here I am. Again, similarly for y negative, I have 7 minus a negative number, which gives me something that's larger than 7, and so that fits well with what I have in the picture here. When y is negative, when it's below 0, then depth is bigger than 7 feet. Great. Now, obviously, I'm not concerned with rho g because that's just a constant. It's independent of anything. I can take it outside the sum and then outside the limit. So that's not a concern here. Now, about AI. So AI is also dependent on yi. What is AI, first of all? Right. AI is the area of the strip that has vertical coordinate yi. So it's this area over here. Right? So now this area, it depends on y, because if I were to look at the strip over here, this strip is longer. Its vertical dimension is roughly delta y, so it has bigger area. So all strips have vertical dimension delta y. They are thin, and their height is delta y. Now, if I look at the thin strip over here, this strip is short. Right? I'm at this tapered part of the circle, and so that makes my area smaller. Okay. So now what I have to do is to think of AI as a rectangle. It has variable width. Okay, so it has variable width, but constant height. And so I have the height delta y and width wi. So it remains to express the width of my thin strip through y. Here's how I do that. Again, I think about this as a circular shape. Right? So I want to determine what is the width that corresponds to distance yi. Right? So what is the length here? If I step away from the diameter, so I have diameter here, right? This here obviously is equal to 6 because I have 2 radii, so that's 3 feet times 2. I get 6 feet. Now, what happens if I step away from the diameter by the distance yi? Right? So what's the red length here? Okay, so what I have to do to determine that length is to connect these 2 points to the center of my circle. And so this is our unknown. And here's how I determine it. I draw the height here. Right? These 2 sides are both 3 feet. If they are radii, I just connected center to 2 points on the circle, which means the 2 lengths are 3. And I have also this length here. Right? This is just yi. And so I have a pair of right triangles. Right? Their bases together give me the red part. That's what I want to determine. And the hypotenuses are both of length 3 feet. So what I'm going to get for wi is this. Wi is the length of the red part. It's 2 because I have 2 right triangles. They are equal. I have 2 times hypotenuse squared minus the known side, which is shown in blue here, squared. All right. And so this is the expression for wi I obtain, and finally I'm ready to set up the integral. Here's what I have. In place of wi, I write, what is it, 2 times 9 minus yi squared. And I have to multiply by 7 minus yi times delta y. So you can see that this is a Riemann sum, an integral sum. When n goes to infinity, I'm integrating 2 times 7 minus y times the square root dy. Now, where is the integration happening? Well, how to integrate from the lowest point of my drum to the highest point of my drum. 0 is right at the center of the drum, so when I go to the highest point, I'm at 3 feet above the center. When I'm at the lowest point, I'm 3 feet below the center. So that means I have to integrate from -3 to 3. So I have successfully set up the integral for total force, total hydrostatic, the pressure, total force of the hydrostatic pressure on this drum. And so I just need to go ahead and evaluate the integral. Now, so first of all, what you want to do is to split this integral by using the distributive law. So here, distribute this product, and then integrate the two terms separately. Now, there is another trick to this integral that I want to show you. Let's see. So when I split this here, I get 14 times the, I can actually take 14 outside the integral. So I have, let's see, 9 minus y squared dy from -3 to 3, right? Minus rho g times 2 integral of y times the square root. So, of course, what you should do in the first integral here is a trig sub, in the second integral a u sub. So if you do that, you will obtain the values. Now, another way to take a shortcut here is to notice that the expression you're integrating in the first guy here is just a semicircle, right? So square root of 9 minus y squared corresponds to the upper half of the circle of radius 3. Okay, so what we are doing is we're integrating this function here from -3 to 3. So the first integral ends up being 14 rho g, obviously, times the area of the upper half circle, if the circle has radius 3, and so that's pi radius squared over 2, so that's 7, that's rho g times 7 times 9, so we get 63 pi times rho times g. Now for the second integral, again, I could use the u sub to evaluate it. That's perfectly valid. Now I can take a shortcut here as well by observing that this function here, it's odd, right? So the function inside the integral is odd in the following sense. So it's, again, a reminder, odd function looks like so. So it is something that looks symmetric with respect to the origin. So say this is the origin, and I must have something like this. Okay, trying to make it symmetric with respect to the origin. What should it look like? Let's say like so. Actually, let's make it a bit. All right, yeah, slow growth, like that. Now, what's the idea here? Odd function satisfies f of minus x equals minus f of x. So that means that this area here is equal to this area here. So when you integrate, you add up two equal areas when you integrate on a symmetric interval, right? So if you integrate from -a to a, then you have two equal areas that have opposite signs. So when you add them up, you get 0. And so the conclusion is that the second integral, being integral of an odd function on a symmetric interval, this here is just 0. There's also a way to use a similar property for the even function. Right, so what's an even function? So that looks like so. So again, we have the axis and then something that's like this. So that the symmetry is now with respect to the y-axis. What this means is that the two areas under the curve here are equal. And as a result, you have that, well, okay, so first of all, the function satisfies f of x equals f of minus x. That's exactly what the symmetry here is saying. And so as a result, you have that integral from minus a to a f of x dx equals 2 integrals from 0 to a f of x dx, right? So all that you can say is that, well, integral from minus a to a is twice integral from 0 to a, because the integral in the left part is equal to that in the right part. Now, for an odd function, you have a nicer way to evaluate it, because you can say right away that the integral is 0 if the integration occurs on a symmetric interval. Okay, so that was a digression about odd and even functions. Using these properties of such functions, we compute the answer to this question, and it gives us the value of the force of hydrostatic pressure. So let's summarize what we have said about setting up the integral for hydrostatic force. So given a shape, right, determine the, well, first of all, choose system of coordinates. So step 1, choose coordinates. Okay, so say, for example, you want to take the y-axis, so you always choose the y-axis to be vertical, because that's what you're interested in. You're interested in the changes in depth. So it's standard choice, and a good choice unless you want to exploit some symmetries of the shape, to use the lowermost point of the shape as your origin. And then once you have done that, you want to find the, so let's say this is the level of the liquid, and this here is some depth d. Then find depth depending on y. So in this case, as pictured, d is the depth at the origin. If you're not at the origin but at a different value of y, so if y is positive, you're somewhere here, and depth is only d minus y. So this here is given by d minus yi. Then you want to find width as a function of y. So you look at a thin strip like this. And so suppose you have a strip like so. You assume its height to always be delta y, and width in general depends on y. So this dimension here is some w of y, which will depend on the shape. For example, we just computed it for the circular shape. There are also ways to compute it for triangular shape using similar triangles. If the shape that's floating in the water is just a rectangle, then width is constant. Okay, and so once you have this, you can set up the integral sum. Right? So f is equal to the sum of fi's is equal to the sum rho times g times di, which we know is d minus yi, times ai, which again is wi times delta y, because this guy here is precisely the area of this green strip we have shown here. And so once you write everything out, you get an expression that is an integral sum, and you have your integral setup. Now, the integration always occurs in the range for y, which includes the shape. So for example, in the picture here, we will be integrating from 0 to this point over here, because there is no shape that's involved in this hydrostatic force above this level. So y1 as setup can always be 0 if you always choose the origin at the lowest point of the submerged shape, and the upper limit of integration will then be y2 determined as in the picture. So we'll have integral from y1 to y2 rho g d minus y f of y dy, and this is how you set up the integral for hydrostatic force.